Hola, Cari.
Hola,
¿Cómo estáis?
¿cómo
¿Cómo te ha
estás?
ido?
Bien, ¿y a ti?
Bien, bien. Acá con
Qué
un
bueno.
poquito de frío.
Oye, igual, hace harto frío.
Hola,
Hola, hola. ¿Cómo, cómo estás?
¿cómo están? Buenas, ¿cómo están?
Hola,
Hola,
bien, ¿y
Karina.
tú?
Hello.
Hola,
Hola,
Hello.
profesor.
Hello.
¿todo bien?
Bien,
Bien,
bien.
con frío.
Frío.
No sé. Es mejor ahora que durante la noche.
Yo ya estoy con parca.
Pero, ya, ¿quién tenemos? Acá está. Dos más. Any questions before we begin? We're waiting on people.
Yes, about the amplification factor, the last part of the last class, it refers to inverse Compton spectra specifically, or we can.
Yes.
Okay.
It's very specifically the inverse Compton. It's
Using
basically amplification by inverse Compton. Right?
Mhm. Okay.
Okay.
Thank you.
Any other thoughts, questions? Okay, so let's begin. So we learned kind of very specifically about a couple of small parts of inverse Compton in terms of the overall power or what the spectrum will look like for a very small. So if we have a small portion of a spectrum, we will see what that upscattering looks like in terms of what spectrum it casts for a very sort of limited amount of say electron speeds and some extra spectrum, right? And so you can imagine that when you have integrating over the full electron distribution in velocity space and the full photon distribution in frequency space, you have to go piecemeal through it to get the upscatter and then sum everything to get what you sort of want. So that's not a trivial process. And so the way by which we do that is, well, one can run the Boltzmann equation. Is this right? No, this is B. This one. So we can sort of generalize this by running the Boltzmann equation. And so we have basically we want to look at the evolution of the isotropic or non-isotropic photon phase space density, which we would consider n omega. And then for the electron momentum and the sort of phase space density of electrons, we would consider this interaction. So we have the initial sort of momentum and the initial frequency of the photon, and we end up with something that comes out which is modified. And so taking into account all of this, what we would measure is the change in the space density of photons as a function of time, as a function of frequency, is going to be related to the initial sort of phase space density of electrons here, the initial phase space density of photons here, and then we want to see what comes out, the final product here. And so we have to integrate this over all solid angle and factor in the cross section for the scatter, and then integrate that over all phase space. And the other thing that we actually need to consider here in some cases would then be stimulated scattering effects, which could be due to Bose-Einstein statistics being able to occupy mutual quantum states. And so there's an extra factor here, which is once you have upscattered and have some extra component, you can get some sort of crosstalk or feedback from this stimulated scatter. And so there's this extra term here, which comes in here and here, because you have some sort of scatter up or some interplay between the upscattered photons and the initial ones. You also have some interplay between the upscattered ones and the initial ones here. So you have both terms here that kind of will balance. As you can imagine, this equation is tricky to solve for very detailed cases. And you have to, this is basically taking into account kinetic theory plus correction factors. And so here you also have to assume that there's a low energy transfer per scatter. And if you assume this, then this equation, the Boltzmann equation, can be expanded just into a second order equation, which is known as the Fokker-Planck equation, which isn't shown here, but it is shown in Rybicki-Lightman. And then the Fokker-Planck equation can be reduced to what's known as the Compagnett's equation, which basically describes a very particular sequence. It's the photon evolution under repeated scatters in a non-relativistic medium, where the inverse Compton is happening off of thermal electrons. So it's a very specific case, but then you have a relatively straightforward, and I'll put straightforward in quotes, equation, known as Compagnett's equation, which looks like this. And so this is the change in the number as a function of, in this case, this is the time between scatterings. So it's related to the time, but it's actually factoring in the cross-section, right? So we've integrated over it and moved it over here. And assume that it's all kind of based on just the number density of electrons. And then we have a sort of temperature of the electron component compared to its rest mass. And then we have this functional form, which is relating the frequency to the kinetic energy of the electrons. And this is still non-trivial and typically needs to be solved numerically. But in some cases, you can make approximations that this term dominates, for instance. And so then these terms drop out, and then this becomes something where you can actually devise a sort of solution by first principles. But in general, you would need to run it through and kind of iterate in order to find a solution for more complex problems. Okay, so there are a couple of limiting behaviors that Rybicki and Lightman sort of outline here. And one of those limiting behaviors is when you have repeated scattering to the point where you get saturation. So you have so many scatterings that all the photons pile up near the energy of the electrons. And at that point, the electrons can no longer be giving energy to the photons without receiving some energy from the photons. So you end up getting an exponential decay at that point. And so you get this pileup, and so you get a huge boost of sort of photon energy, which kind of looks sort of like a black body peak. And you have sort of one side, which is where they're all piling up from, and then you have the other side, which is the exponential decay. And so in this sort of limit, the saturated spectrum will have a high frequency end, which will look like a Wien law. And so as this process is happening, before it reaches complete saturation, what happens is you'll have the modification of energy as a function of this TC, which is the scattering time, or the time between individual scatterings, you'll see that the energy increases as basically this sort of integral. And we can do out this integral. X here is again just, where is it? Yeah, just this. And so we do out this integral and we end up with something which looks like this. So this will increase, the energy will increase as a function of scattering time as this sort of power. So it's related to the electron velocities or the electron temperature in this thermal regime, and then the energy, the initial energy of the photons. And so you'll see that it will sort of increase, and then at some point it will saturate. And this particular solution, again, neglects these two terms and it's dominated by this dn dx term. And so what will happen here is you end up producing a soft, basically if you have the total energy here in sort of a soft input spectrum, so X is much, much less than 1, the photons are much less than the electron energy, this will then increase initially as this. That's what you can see if you put E on this side, you put T on this side, and you integrate, you have TC here and you have 1 over E, you integrate that, you'll get ln E. And so then taking the exponent of both sides, you get something which looks like this. And so the energy will increase exponentially following this scattering factor. And this is similar to this previous form that we had mentioned, where you have the initial energy and you have some exponential to this Y comptonization factor to get your final energy. So this is sort of a similar version of this. And here we're replacing the tau here with this TC instead. Okay, so in general, we can think of two regimes, and one again was the saturated regime, which we call saturated compensation. So Y here is much, much greater than 1, and generally all the photons are scattered up to the maximum through repeated scatters. And then you have another regime where you can calculate things, which is what we call a sort of modified black body, or if we have a thermal distribution here and we have a very low number of scatterings or low comptonization, then we can approximate this analysis. And in doing this, these are regimes where we have repeat scatter off of non-relativistic electrons. And so these are two cases we can solve. There are intermediate cases, which are unsaturated compensation. And there you have to have a detailed treatment of it. And you can kind of make some approximations under, I would say, optimistic or simplified conditions, but it's still a little bit tricky. And we can delineate the regimes between these sort of three cases, or delineate the regimes where we might expect inverse Compton versus regular scattering versus no scattering at all, by highlighting a few in sort of characteristic frequencies. And here we'll assume that the input spectrum of the photon is from free emission using a Roslin mean expression. And so, we have a distribution which is sort of, it has the optically thick component, the optically thin component that's flat, and then the cutoff. And so in this case, we can define a frequency nu as the point where electron scattering and free absorption are equal. And so basically above this frequency, scattering will be dominant, and below this frequency, absorption will be dominant. And so at this frequency, we can equate the absorption coefficients, which are now given in kappa here as opposed to in alpha. And basically we have that in the absorption regime, this thing can kind of be expanded to be this. And so it'll go as temperature to the -7/2, and the density of the material, and then this Gaunt factor. And the Gaunt factor is this very loose sort of dependence on nu and t. And so basically what happens here is that if we have Bremsstrahlung free, absorption is going to be most important at low frequencies. And so if frequencies are lower than this, absorption dominates. If frequencies are above this, scattering is important. And this sort of defines this interaction, first transition point. Then we have another transition point where the medium becomes optically thin. This is sort of the turnover frequency that we had before. And so here we can equate the absorption coefficient for scattering with the free coefficient in this sort of regime where the scattering is still somewhat optically thick, so we go as tau squared, and this is tau is the opacity to electron scattering. And so in this sort of regime, we have now again the same sort of functional form, but putting in this frequency, this will be roughly equal to this. So we have this extra factor here of tau squared. And so in general, if the frequency is higher than this, then absorption is completely unimportant. We're in the optically thin regime. And so if it's in between these things, then we have scattering and absorption are both important. And so above this, we still have that scattering could be important. And then there's a third frequency here, which is called the coherent frequency. And the coherent frequency is basically when inverse Compton can start becoming important towards modifying the spectrum. And so generally speaking, the energy gain is going to be comparable to the original photon energy here. And so we can define a frequency such that this amplification, this Comptonization at this frequency is equal to 1. And so for frequencies that are higher than this, this is going to be larger than 1. And so we're going to have an amplification, right? So we're going to more than double the energy, and we're going to modify the spectrum. And so inverse Compton is important up to the point where this thing can then, the photon can just escape from the medium, and therefore we no longer have any scattering. And so then in this case, we would equate this absorption coefficient with this factor here, which is this amplification, or basically the factor by which we amplify, and then this free coefficient at this frequency. And so you can see that the point here is that this coefficient, this absorption coefficient, depends on the input spectrum, right? And so that's why it's being modified at these different frequencies. And so you get these regimes where you have different scattering properties as a function of frequency. And so here, we're in the optically thin regime, so this thing is going to be approximately given by, the spectrum would be approximately given by this thing. And this again is only when y is greater than 1. If y is always less than 1, then you don't have scattering, and it doesn't really matter. You have your initial case of Bremsstrahlung. Okay, so this is a lot to take in, and it'll be helpful to actually visualize this a little bit better. And so we can have a specific problem, which is let's say that we have a relatively, well, we basically have a spectrum that looks like free, and we have the case that the intensity here is going to be proportional to the black body, and then you have this extra factor here, which is related to the absorption coefficients. And so you have basically that you have a modified black body, which is approximately equal to this thing, right? And we can plug in what this is, and we get out something which looks ugly, but it has the right form. And we can define the frequency regimes that are important here. And so we have the frequency regime where absorption dominates. And so basically what this should reduce to is just this should be equal to this at low frequencies, right? So we just have our nu to the squared power. Then we have someplace where scattering becomes important. And so we have that the intensity sort of moves into this modified black body form, which looks like this. Then if we have this frequency is less than this thing, then we have a situation where we have, if nu is less than, remember this is the optically thin portion. So if we have this optically thin frequency is below the frequency where scattering is important, then what we have is our regular absorption, and then we transition into our regular optically thin portion up to the point where we might have scattering be important. And so the spectrum would look like this. And so we'd have something that had this sort of form. If this sort of frequency, this optically thin frequency is in between the scattering frequency and the peak frequency. So we have some place where scattering is important and some place, then we have a turnover, and then we have some place where it peaks out. What we end up having is three regimes. We have the absorbed regime, we have the modified black body, which happens in between here, and then we have an optically thin case where it escapes pretty easily up to this point. And so this thing here ends up being proportional to nu, not to nu squared, as would be in this case. And so you get a bending of the spectrum before you get to the optically thin flattening. And then finally, you have a case where if this frequency is greater than this, then you would have just these two regimes, since you would never get into the optically thin regime. You just have a modified black body. And so this kind of shows what this is talking about. So we have below nu naught, we have just our intensity is going as nu squared. Above nu naught, we have the intensity is going as a modified black body, so as nu. And then we have at some point here is our optically thin regime. And so we break into an optically thin regime, which is here. And so we have nu going as nu to the minus 0.01. And then we have our exponential here, which dies off after we more or less, sort of run out of energy from the electrons that are doing the upscattering, or not upscattering, or generating the photons, and also doing some of the scattering here. So this is what this would look like. It's just a modified black body, right? So it just stretches it out a little bit. And that's just you get a small boost from the inverse Compton, which stretches it out. Is everyone following this? It's not trivial. Okay, I'll take your silence as yes. Okay, so there is another case here where we have full saturation. This is called, when y is much, much greater than 1, we have many, many amplifications. And so we end up getting a pileup at the sort of peak of the spectrum. And so when this is important, when y is much greater than 1, then the third frequency, the coherent frequency, becomes important. And this is the point at which the scattering is no longer coherent. By coherent, we mean sort of phased or forward scattered. But basically, the inverse Compton then becomes a very important process that completely modifies the spectrum. And so basically, scattering is always coherent when this thing is greater than 3 kT. Right, because coming back to here, the spectrum will have an exponential fall off around 3 kT. And so if the coherent frequency is up here, then it doesn't matter. Right? It's only when the coherent frequency moves below this that we start having inverse Compton being important. And so IC will occur when this happens. And when this happens, then we have our spectrum will start behaving like this. So we have our input frequency and we have our output frequency, and we have this amplification term. And so we're going to get basically what will happen is if we take the previous case for frequencies below coherent, we're just going to get the same thing, right? So wherever this coherent frequency is below that, it's the same thing. Above that, then we get a modification because we start completely upscattering things because of this. So IC will start to saturate when this condition holds. And so we can think about this, the intensity will be characteristic of this intensity here, which we say is the Wien intensity. And so it will look like this thing and this thing, which is our classic sort of black body. We have this extra factor here, which is this exponential. And this is related to the rate at which photons are being sort of produced and upscattered, right? And this is, recall our factors here are tau and our amplification factor. And so in this sort of situation, the total flux here would be just integrating the Wien spectrum over all frequencies. And so if we do that, we end up with something which looks like this. And so we have basically KT to the 4th power here, and this amplification factor here that ends up all of the sort of spectrum above this coherent frequency is thrown into this flux component, which is all piling up near the electron energy. So typically the mean photon energy here of the spectrum is going to saturate roughly at this value. So you get a pile up here. Okay. So as this is occurring, basically you have a rate at which the energy is being generated in the Comptonized spectrum. And we can estimate this by shifting all these Bremsstrahlung photons to energies of a roughly KT. And so what this means really is that we have some amount of energy in this Wien spectrum as a function of time, as a function of volume, that's going to go as KT, and then this integration of this emissivity divided by the average energy here and integrating over these. What we can do is decouple this and sort of move this out. And so we have something which has a sort of, we've taken all the energy, and because it's all piling up around 3 KT, we can remove it out. And we have a mild temperature dependence from the Gaunt factor, and we have our exponential here. And we would just integrate between some frequency, basically it's a 1 over frequency, integrating between the coherent frequency and infinity. And this is going to give us the total amount of work done as a function of time, as a function of this total volume. So this thing, we can approximate it if we evaluate the Gaunt factor at this lower limit, the coherent frequency, and we basically let the exponential here become a step function that is unity for frequencies less than KT and is 0 for frequencies greater than KT. And so in that case, this integral then becomes something very simple, where you just have an amplification factor, which is based on the density and the temperature. And this thing is approximated by the log of this, where you have, this is at the coherent frequency. And so what happens is this is an amplification factor, which takes the Bremsstrahlung power, dumps it roughly at KT with some total power and amplification. And so the emergent flux here, it's going to, basically what we have to do is multiply this equation by a characteristic depth. And so if the frequency is still in the optically thick regime, so this is less than 1, let's see, if this is less than 1, is that right? If this is much, much less than 1, is that going to be optically thin regime? I'm confused. Let's see, let's go back. Okay, so xt is the frequency where it becomes optically thin. Ah, okay, yeah, okay. Right. Okay, so if the thing so the frequencies are less than the KT in the electron, so there's a huge range between the optically thin regime and the overall energy, then you're going to have a medium which is optically thin and you can upscatter. And so you're going to have that the total flux coming out is proportional to this energy and then the size of the medium. Because it's optically thin, it's only going to have an upscatter and then it's going to leave. if the optically thick regime is much greater than this, so basically the entire portion of the Comptonization is happening in the optically thick medium, then what's going to happen is that this frequency above the coherent frequency, you're going to get an amplification to x approximately 1. And so instead of using the entire medium, you're going to use only the portion of the medium, or the size of the medium, where you get the full upscatter. And once you get to KT, the process no longer really gives you anything. And so you can approximate, instead of R, you would replace this with R sort of bar here, where R bar is the point at which tau equals 1, where you get this scatter up to this point. Hopefully that makes sense a little bit. You should see it a little bit better here. So we have our point where below this, we had our original spectrum, right? So we had our optically thick regime, we had our optically modified blackbody regime, and then the coherent frequency happens to be here. And so what happens is, this is the point where Comptonization is important. And so we have a lot of photons which are getting upscattered, 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 and you get a pileup of the energy which comes out here, roughly at 3 kT divided by h. And then above that, you get this exponential cutoff. And so this is not super intuitive, so it might be, this is a little bit more helpful. So you take, for every sort of small subset of frequencies here, what happens is you get a scatter. And so you have something which looks like this. And you drop that down by a factor of tau. And then you have some fraction of these photons will be amplified and upscattered, 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 upscattered. And then most of the photons accrue up here. And there's no more upscatterings that can happen. So you have this thing, which is then upscattered up to this, and then you have most of those are depleted because they're scattered again. So you scatter again, and then most of them are depleted, but you scatter again, and so forth. So all of these are the individual scatterings up to the point where you can no longer scatter anymore, because the electron no longer gives you any energy. And so you have, this is all this related, this flat portion is just related to tau, what tau is, and then this is where most of the energy comes out. And so coming back here, this isn't flat because we're in the free regime. This is flat because tau is very, very large, and you're getting a drop every time from this number of photons down to here. And all those photons are being upscattered again, amplified, and then you're getting a drop, amplification, amplification. So this regime here depends on the tau, which can be frequency dependent. It doesn't have to be flat. It could be something like this, it could be something like this, depending on exactly what the frequency dependence of this was, right? Which we came back way back on ago here. This thing does have a frequency dependence. And so this amplification is fine, but this thing might, the scattering probability might change a little bit as a function of frequency. Okay, is everything clear about why you get this sort of spectrum?
More or less. For me, I was like a little lost. I didn't understand very well why, in the part of the almost flat spectrum, the Compton scattering is amplified the emission, but then is decreasing the emission. I didn't understand very well this.
So in this particular example, so tau is not greater than 1 in that you take this and you upscatter it and you get this spectrum coming out of that, right? So that's the initial scatter. And then those photons are still in the medium and they're susceptible to being upscattered again. And the medium is optically thick. So they travel through the medium and they interact with another electron and they get upscattered again. And this decrease here is the probability with which those photons will be upscattered, right? And so this is a huge factor. So most of the photons are upscattered, and typically what happens is that around the edge of the medium, you'll have them escape, right? So some of these photons escape just because the structure of the medium. But let's say that it was tau greater than 1 for most of the medium, but at the edge of the skin, you get some escape. So these escape. The rest of the photons are upscattered again by an amplification factor. And same thing happens. Although the edge of them escapes, right? So you get this, but then the rest of them are upscattered again. And so on, and so on, and so on, up to the point where the energy of the electrons can no longer give the photons any energy, right? The photons basically have a similar energy as KT. And so what happens is you just those photons end up leaving because the medium just becomes optically thin instantly because of that. And you might have some case where, well, actually, there's a frequency dependence here, and maybe this doesn't fully upscatter. There's some more escape from these. And so you might have something which smooths out in reality. But this is just to give you a kind of extreme case. Does that make sense, man?
Yes. Thank
Okay.
you.
We must depend of the electron density also, right?
Yeah. But this is the electron density is going to come into tau here, right? So if you're in the optically thick regime, well, actually, you can be in. I should say it wrong. So you have the input spectrum, which is dependent on the optically thin and optically thick regimes of Bremsstrahlung. And then you have, coming back here, you basically have that this sort of the absorption coefficient for scattering. And what's happening when I say absorption coefficient here, what I'm really meaning is that the photon is susceptible to a scatter, right? And that scatter, that scatter can impart an additional energy to it, but it isn't going to impart much. And then above the coherent frequency, then you start to get amplification. And so this is just a simple scatter, which depends on tau. And so you end up just sort of increasing the energy a little bit. And then at this point, you fully start to enhance the energy of the photons by a large factor each time. And so this still depends on the electron density, right? So this still depends on the electron density.
Mm-hmm.
And so the same process can happen for synchrotron as well, right? So the synchrotron, and we'll come to that in a little bit, but you have something that generates, in this case, you have the electrons, and typically the electrons that are generated from the Bremsstrahlung, you will have a little bit of upscatter, you modify it a little bit. The same thing can happen with synchrotron, but the synchrotron electrons are have a relativistic distribution, and so you can get a lot more upscatter from them. And so we'll have a look at that in a second. Then there's a third case, which is that you have a population of electrons, whether they be from synchrotron, from thermal Bremsstrahlung, and you have a photon distribution which is decoupled from that, say the CMB, right, which is one of your homework problems. And so there you're looking at an interaction between a completely distinct separated thing, whereas this process here is actually sort of self-upscattered in a sense, right? Because you have the free photons which are being generated, and then the medium is potentially modifying it as well.
Mm-hmm.
And the same with synchrotron. You have synchrotron, what they call self-compton. So in the same medium, you create the photon, and then the same electron which has created it is also upscattering it.
Mm-hmm. Thank you.
In general, these are, this is a fairly this is probably the most complex topic we will get into. Although I won't say necessarily equally annihilation and pair production is also complex, and we'll deal with that shortly. But wrapping your head around this, because it's nonlinear, is a little bit tricky, right? And so I'm not asking you to solve some complex thing, but just to kind of understand what goes into it. Because unless you're dealing with like radio jets or Sunyaev's effect or something, you're not going to experience this too much. Okay, let's see. My headphones are asking me to charge, so I'm going to go get a cord. I'll be back in a second. You guys have a quick mental rest. Okay. Any other thoughts, doubts? Do people feel like they understand it or that they're completely lost? Most of you are saying, I'm pretty lost. So what are you lost about? Can you articulate that? And if you need to ask in Spanish, that's fine.
At least for me, I didn't understand like the plot. I understand like, okay, I'm upscattering until I reach like this limit of energy the electrons can give to the photons. But I'm still not sure what process could lead to this like I don't know this I forgot the word, like this saturated comptonization.
Comptonization, yeah.
Like
I mean, all you have electrons, which are they're non-relativistic, but they have energies which are, say they're coming from a cluster of galaxies, right? So they have temperatures of 10 to the 8, which are technically not relativistic, but they're pretty high. And so what happens in this case is you have low energy photons, which are sort of doing something. And then as you get close up above this coherent frequency, then those photons in particular can interact with the electrons and gain a lot of energy from them and they'll cool the electrons too, right? And so depending on the exact shape of the medium and everything, you will get out some spectrum. Like in this case here, right? Like there is another version of this case. Let me find my pen here. So imagine we had something which was just completely optically thick and there was no escaping. Where's my draw? There, the draw. So there's no escaping from the medium at all until you get to this point. And so then what would happen here is that you'd have something which dropped off at this coherent frequency, maybe even further, where all of these photons are being upscattered to this point, right? And then you just have this. And so, depending on the medium, you might have something different here. And this was only an example where, it's sort of a realistic medium where you're going to have some escape from some fraction of the photons. And that is going to be relatively constant because it's just sort of the skin of some region. But if you imagine that the skin was infinitely thin, then what basically what you would have is, let's see, clear all drawings. Yeah, you would kind of have this go like that, and then you would have this come up like this, right? And maybe that's a little bit easier to kind of think about, in that above this frequency, all of those photons pile up here. Right? And the only issue is just in reality, you never can have that extreme case. And so you end up filling in something here. And I mean, I think that sort of explains that. The other one, which is, get out of this mode here. Let's see. I mean, so this one, I think, is also relatively easy to see, just because we don't have a lot of upscattering. And so we're going to have just we have some scattering here, which modifies this a little bit, but it's not energetically that important. It's only a sort of a factor of 2, which is what makes this thing go from a nu squared to a nu, more or less, right? And so it just stretches out the spectrum a bit. And then we don't really have a regime which is optically thin. And this really all depends on exactly what the details of this are, of where these frequencies fall. And these frequencies are dependent a little bit on you know, the internal makeup. What are the products that we have in terms of the electron distribution, the density of them, and the photon distribution. And those are the ingredients, right? And then you mix them together, and you're either going to get something that is, you have some scattering, which is important, or you don't. And then the scattering may be to the point where you get inverse Compton from it, or it may not be. Okay.
That helped a lot. Thanks.
Okay, good. Okay, so right, so we got to here, and that was fine, or here rather. And so then there's, I guess, a sort of intermediate case, and this is a little bit trickier because it really depends on the situation. And so here we have unsaturated comptonization. So for instance, y can still be greater than 1, but the coherent frequency, for instance, is close to the energy. And this means that inverse Compton will be sort of important, but you don't get a huge pileup of sources. Another possibility could be that you have y isn't greater than 1. This wouldn't be comptonization, because comptonization requires y to be greater than 1, much greater than 1. The sort of technical term by it is just that all the photons are upscattered, right? That's what comptonization means. And so you could have a case like this, where this was equal, and so you just don't have that many photons to really make a distinguishing spectrum from the original one. And so what that would do here would just be to sort of modify this, annotate it again, and so you just have something which looked like that. And so you don't really have much of a pileup here, right? Because the coherent frequency has been shifted up to sort of here. And so you get something which sort of modifies the exponential a little bit, but it'll be subtle. So that's that case. Okay, and then there's this other case here, which is you don't really have comptonization, but you have some upscattering. And so we can ask sort of, okay, what happens if y is 1 at a frequency that is comparable to the energies of the electrons? And so basically what that means is y is 1 near this coherent frequency. And so the electrons aren't going to have enough energy to saturate the spectrum, right? So you don't get the Wien form at all, but you do get some modification of the spectrum. And here's where we really need to rely on Companet's equation. And so Rubik and Leibman do this for an idealized situation, which is this. And so generally speaking, you have, for frequencies much greater than kT, you have the exponential fall off. For frequencies less than kT, what happens is you get a modified spectrum, where the modification takes the form of a power law. And so basically you have once you get to a steady state, basically what you have some soft input spectrum here. And so photons where this frequency is less than this have this initial spectrum. And then in between this frequency here and this here, you end up with a spectrum which has a power law here, which is related to Y, which is approximately 1. And so this is 4. So 9 halves plus 4 halves, let's see, that's 16, 19, 25 fourths. So it's about 6 square root is about 3, not 3, 2.5, something like that. And so you have this thing plus or minus this thing. And so generally speaking, depending on exactly what the Y is here, you might have one solution which dominates, and you take that, or you might have a linear combination of these two, which kind of cancels out. And they just give an example where you have something which ends up giving you a spectrum which kind of looks like this. And so the initial spectrum here is not super critical, but the issue is just that you get a dependence here which is on this very sort of weak compactization. And it's you need to have a lot of idealized conditions here for this to apply. And so it's, in real life, you probably won't have that. But you might have something which modifies the high energy end of it. That's the main point. Okay. So that's basically all Rebecca and Lightman have to say on this. One very important extra item here is dealing with synchrotron self-compactization. And so here we have a population of electrons in a magnetized region. It's generating synchrotron radiation. The electrons are relativistic. The photons might be in a regime where they can, the cross-section for compacted scattering is not 0. And so what happens is you can have some probability that once you created the photon by the electron, an adjacent one might be able to upscatter it again. And so in general, basically what you can think about is that the electrons are doing twice the amount of work. They're creating the photons, and then they're transferring some more energy to the photons via inverse compacting. And so this sort of process is called synchrotron self-compacting, or SSC. And so the degree to which this occurs depends strongly on the electron densities, and the photon densities. And so the places where you can imagine this happening are in radio jets, right, where you have some very, very compact region of relativistic electrons, and they're generating photons in a compact region, and so there's an interaction there. The electron distribution will go as this, and actually what we expect is that the SSC flux will actually go as k squared. So again, you can see that the electrons doing work twice comes from this k squared term. And the way you can see this is the following. So let's imagine that we have a synchrotron source that's radiating synchrotron. And we consider the synchrotron energy density will go like this. So we have the luminosity of synchrotron over some volume, right, to give us the density. And then we have, this is related to the crossing time, the photon crossing time, which will give us some estimate of this energy density here. And so we can think of this as this photon crossing time times the emissivity of synchrotron. And so we can play this trick that the emissivity of synchrotron is just a normalization times the frequency dependence, right? Which you guys did for homeworks or in the exam. So that's fine. This is just the magnetic field and this constant here and so forth. We can think about the emissivity of synchrotron self-compacting. So the upscattered component is going to be related to the input emissivity, the optical depth for this scattering to happen, right, which we say is TC, some normalization factor, and then we have a frequency dependence, which is at this critical frequency where we're going to start to have, this is the Compton frequency, or the where scattering is going to be coherent. And then we have this extra dependence here on 1 over this frequency. And so, we're dividing this like this, right? This is where this comes from. And then we just want to figure out what our emissivity is for synchrotron self-Compton, SSC. And so this thing here is going to give us a logarithmic dependence on frequency. And we can call this new capital lambda here. And so this thing is going to look like this. And so this is dependent on the emissivity, it's dependent on our tau here, and it's a very loose factor here as well. And so we can kind of roughly take the ratio between these two is going to be related to this, right? This is roughly 1, more or less. This thing is going to have a dependence on the electron density, the size of the region, and the cross-section for Thompson scattering. And so this thing has this dependence. And so generally speaking, there's a K here, there's a K here, and so this is going to be proportional to K squared, plus some dependence on the magnetic field and some dependence on the size. Right? And so a typical example would be, here's our synchrotron source, and we have some place where it's absorbed, right? So nu goes as 5/2. We have a turnover frequency, we have an optically thin regime, and then at some level the electrons die off and we get a decline. And so the upscattering will, in this regime, so each one of these things will then give you one of these, right? And so when we integrate over this, we get a bunch of these different things. And so we actually see that the slope here is going to mirror itself in the slope here. We get a factor down, which is proportional to our tau and our ln lambda here. And then at some point, we will also get a turnover here, which is partly because of this, but you can see that it's broadened, and that broadening is because of this extra term. And so this is the inverse Compton portion of this initial input spectrum. And so if we looked at a source, we might see, okay, if we had a cutoff here, we might see a spectrum like this. And then if we had sensitivity to X-rays or gamma rays, we might see this component. And then we could compare these two and say, we have synchrotron self-Compton. And that tells us something about the distribution of the electrons in the photons. Because you wouldn't get this if the electrons are distributed too widely, for instance. Okay, so if we're pretty confident about a particular source being related to the synchrotron self-Compton process, we can actually use a couple of simplifications to place constraints on it, which are actually pretty interesting constraints. So, we already know that the synchrotron spectrum is going to be self-absorbed, and that part of the spectrum is going to give us the B field, right? So the optically thick portion is going to be proportional to this. The optically thin portion is going to be proportional to this. And so we can get our magnetic, if we measure the size, we can get the magnetic field out from this, right? And we don't necessarily need anything else. And then once we have the magnetic field, we can get out our K factor here and our R, which actually this thing is just tau. And so we would be able to get out this component. And if we made some assumptions, if we knew the distance, then we could figure out R. But we don't necessarily have to know the distance to get out this factor here. And so we can actually use this even though we don't know the distance to the source, which is convenient. And so in this case, we can, this is a common thing that is employed with radio log AGN. And so you can, we have some source, we see self-absorption frequency, we can measure it here. And that gives us the optically thin and optically thick regime. And we can figure out the flux at this by simply measuring it, right? So we know some flux FT at this frequency. So we can rewrite these equations as the magnetic field goes as this turnover frequency, so the turnover frequency, the turnover flux, and this thing, the size. So if we measure the size, we get the magnetic field. Once we have the magnetic field and the size and the frequency and this flux, we can get tau. Once we have these two, then we should expect that the flux from synchrotron self-Compton will go as this flux here at some critical frequency c times tau, and this thing should be proportional to this. And so we potentially have a measure of this, we have a measure of this, we have a measure of this, so we can actually predict what this is. Right? And so written in other terms, this is the flux at t, the frequency at t, the size, and then this critical frequency, the coherent frequency. And so with a few observations, we should be able to calculate the synchrotron self-Compton flux at this critical frequency. And so this is a very strong dependence, right? On the size, on the frequency, on the flux. And so this, what's sort of interesting here is that, okay, when we do this, basically what this is saying is that, if the source is more compact, so the size is smaller, if this is smaller, this is inverse, right? So this is 1 over this. That means more compact sources are going to generate a hugely stronger SSE signal, right? Which makes sense. You have a denser source, you're going to get more upscattering, and it's going to be more optically thick, so you're going to get potentially higher scattering, higher compensation. Okay, so if we observe the higher frequencies, we can say, okay, do we expect SSE signal to dominate? And we can check if this model works. And so we ask ourselves, does it? And so it turns out for the strongest radio sources, it doesn't work. There's a huge disagreement here, between what's predicted and what's actually observed by many orders of magnitude. And so what's wrong here? What have we missed that we didn't figure out or we didn't take into account?
The magnetic field.
Well, we have the magnetic field. What we didn't take into account is the beaming. And then typically we're going to see sources that are beamed towards us. And so there's an extra factor there that comes into the observed flux that we see, right? By a delta of 3 or something like that. So it's a huge factor, right? Which leads to this many orders of magnitude problem. And so assuming we're missing something here, that missing thing is the relativistic beaming, the relativistic motion of so we have these blobs of material that are moving relative to us, right? And typically they're moving towards us because we see those. The ones that are moving away from us are beamed away from us, we don't see them, right? So we have to account for the fact that there's enhanced flux and blue shifted frequencies, which we're observing, and then we have to go back to their frame and do all the calculations again, and then see what we get. And so we have this extra factor here that we need to account for in the observed frequency, or the flux as a function of frequency, which is huge, right? This Doppler of 3 plus alpha, and alpha could typically be 0.7 or 0.1 or something like that. So we do that, and so then we end up having this functional form in the optically thick and optically thin regions again, where we have this Doppler factor now, which comes in, and that extra factor here. And so then we predict the SSC flux, and it goes like this, and there's this extra Doppler factor here, which you can see if this is large, this is 1 over the Doppler factor, so much less flux than what's predicted. And so then it matches, hopefully. But what's interesting is actually the thing that's unknown is this thing. We didn't know that before necessarily, right? And now we're actually able to measure it. We're able to measure the bulk velocity of this material coming towards us. And so we can use this as a way of estimating what the bulk velocities are in radio jets by comparing the synchrotron self-Compton expectation to reality, right? Once we measure the synchrotron absorbed and unabsorbed regions, which is pretty cool. But of course, this makes it trickier because there's an extra factor in here that means that the equations are not degenerate, and we can't fully solve everything because we have this extra unknown. We just have enough equations to kind of solve it, but we can't oversolve it and like check necessarily cross-check things. And so obviously there might be uncertainties on exactly what the structure of the material is and so forth that lead to degeneracies here. And so hopefully with all of this now, then coming back to the thing that we talked about, the paper I talked about last week on Thursday, you can start to see the complications of trying to figure out whether a source of high energy protons are leading to an inverse Compton scattering signal in the gamma ray regime, or if it's electrons, and all of the different things that sort of come into play in terms of these high energy sort of PeViatrons. Okay, any questions here? This is just an example of what this looks like. So you have the individual sort of, so this is an example of a composite spectrum. So this is along a radio jet, and each clump of the radio jet is giving rise to an absorbed portion, an unabsorbed portion, and then the energies fall off. And whoops. And then different portions of the jet are giving you different portions in frequency. And then, so the sum, what you actually observe, is a flat portion here, an absorbed portion, a flat portion, and then a declining portion, and then it falls off. And then each one of these portions of the jet is leading to some inverse Compton, which is giving something which then looks like this. So this is like a typical spectrum of so for a flat spectrum radio source, this is what you might expect to see is this absorbed portion, the flat portion, the declining portion, and then an inverse Compton portion. And so if you can decouple all these things, right, if you can resolve the jet and start to see these things, and so typically people are using VLBI at 22 gigahertz, for instance, to do this, they can start to measure the angular sizes of these and really start to pick apart what's going on with these sources. Here's another example here. This is a radio jet from, let's see, this is Centaurus A. It's only at 4 megaparsecs. And so you see the bubbles, which are coming from X-ray hot gas and the jet. And then the jet is filling, it's basically blowing a bubble. And so you're seeing that in the X-ray, you also see it in the radio. And so you can do VLBI, measuring the jet as it comes out, right? And so you see that there's a synchrotron portion here, and then you also see that there's an inverse Compton portion. And depending on your models, you have different models for what this looks like, and they'll make different predictions, right? And so you can compare that, is it matching the slopes in the gamma ray regime around nu of 20, and then the radio regime here. And you also see it vary over time, which is pretty tricky. So this is, for example, a model with gamma of 15 and a Doppler boost of 0.3. This is gamma of 3 and a Doppler boost of 1.2. Right, so along our line of sight versus the intrinsic bulk motion of things. And this is what the actual spectrum looks like. So you have to take something which looks like this, and this is the model for it, right? And try and match that. And then you can do that for individual, you can try and do it for individual clumps. In the radio, you can resolve them. In gamma rays, you can't. And so you have to assume that all the radiation is coming from this particular clump and not this one or this one or this one. And so it's super tricky to really decouple all that information. But people are trying. Here's another example showing variable jets. So this is, you'll see, this is 3C4 54.3. This is 93, 94. You can see the jet actually moving. This is in milliarc seconds. And this is 96, showing again this portion here. And so over that particular time, you can see, okay, the supertron didn't change too much, but you can see that the inverse Compton did. And this is the variability. So this is the variability in the radio, which is pretty smooth, right? It varies by a factor of 2, not much. This is in the optical band, which is roughly right here. And so you can see pretty high variability, probably from the tail of this. And then in the gamma rays, right, you're seeing variability by factors of 300. And that's because you're seeing these individual spots, and the orientation of them and everything leads to this inverse Compton upscattering. And so it can be, you can see huge variations here for what seem like a very little difference here in the radio flux. Right? And so you can place constraints on the geometry of things from that. Okay, the final topic here, I don't have any time left, but basically the final topic is the Zanaev-Zilovich effect. And so here what we have is the electrons, non-relativistic electrons from a cluster of galaxies, so Bremsstrahlung emitting hot gas at temperatures of 10 to the 7, 10 to the 8 Kelvin, or keV, sorry. No, not keV, 10 keV, so 5 keV in energy. And then you have the cosmic microwave background. And so the microwave background should be uniform, but it passes through the cluster. And the hot electrons in the cluster upscatter the microwave photons, right? And they displace them in frequency, shifting their distribution. And so this, what it does is it causes an apparent drop in the microwave background below the peak and a rise above it. So you get things that are on the lower end of the peak, which are upscattered onto the higher end of the peak. And you see that as depending on the frequency, as a negative splotch on the CMB, the otherwise smooth CMB, or as a peak, depending on if it's below the peak or above the peak in frequency. The effect is super small. It's only a change of about 10 to the minus 5 in terms of the temperature variation, but you can use that to estimate the density of electrons and thus something about the mass of the cluster. And so this effect involves multiple scatterings and a change in the photon population number, and so it's described by Kompanyet's equation. And so if we have radiation, which is in thermal equilibrium with a gas, then of course there would be no effect here. But the issue is that the microwave photons are not in equilibrium with a hot gas. They're different, right? So even though both are thermal, they're at completely distinct temperatures. And so you end up getting an upscatter that isn't equated by a downscatter, which if you had the photons which were created by the same medium, you might have an exchange of energies in both ways, and you never see a full upscatter, right? So that's the reason why we end up seeing this. And this gives an estimate of the cluster's physical dimensions along with their mass potential. So what's happening here? So we have a photon coming in, it interacts with the electrons, and it's blue shifted. And so you get, this is not really to scale, but basically you have the incoming photons here, they're moved up. And so you end up having a decrease in this portion here and an increase in this portion. And there's a very tiny shift. This is magnified by a huge amount. Okay, so how will we actually calculate this? So what we want to do is solve Kompanyet's equation. And so we want to solve dN dt in the limit where this photon frequency is much less than the electron energies. And we have an isotropic distribution of electrons and photons, so Kompanyet's equation works out well. We can think about this Kompanyet's equation, we can simplify it to dN dy, where y here is now related to T and the cross-section to Thomson, the number of electrons, and the relative electron temperature. And so y here is sort of proportional to the optical depth. So just a way of rewriting Companion's equation. And we're just going to take the simplified version of Companion's equation. And so we take the derivative of the first two components here. And so we have this double derivative of the number of photons, whoops, and we have the single derivative. And so if this gas is optically thick, we have a uniform kinetic temperature, we can integrate along the photon path, and we can relate this thing y to the mean optical depth here. And so solving this equation, we basically want to find the incremental change in this number of photons as a function of the input number of photons, right? So we want to find the change in this over this. And this thing here, basically what we're going to do is we want to find this over the optical path tau. And so we substitute in our expression for a black body occupation number. So this thing, the number equals this. And we also can redefine our frequencies as a function of the temperature of the CMB is X here. And so we plug that in, we plug these in, substitute in them, and we get out something which looks like this. And so we have our exponential form here, and our double derivative and our single derivative here. And so we want to now figure out what this is. We can estimate that this thing is going to be roughly proportional to a change in the frequency divided by this thing. And this dx here will roughly be a change in the temperature. And so it can be roughly sort of characterized as a change in the temperature divided by t times this original frequency relation here. And so this thing, this ratio, we plug these in, and we end up with this thing is just proportional to this delta t divided by t, and that's proportional to this factor of y here. And so it's proportional to tau, ultimately. Okay, now this is of course, this tau is proportional to the number of electrons along the line of sight, right? And so that's a critical component. So the number of electrons, and if you have some volume, then you know the mass. And of course, the more massive things, right, more higher number density electrons are going to have a larger effect. So a larger delta T. And so ultimately, when you see a change in the temperature, this is a function of the number of electrons that are there or the mass of the cluster. It doesn't have anything to do with redshift. There's nothing in here that is very redshift dependent, other than there will be a slight dependency on the frequency of where you see this shift, but not too much. Right? There's a frequency dependence here, which is redshift dependent a little bit because it happens at the cluster. But other than that, this ends up being a mass dependent cut. If you can have a temperature limit, a sensitivity to a fraction of a temperature, you can see this. There's something going on in Roy's background. Okay. So we now have an equation where if we see a drop in this temperature, right, this should lie just below, or sorry, this should lie just above in terms of wavelength, the microwave peak, or below in terms of frequency. If we see an increase in TB, it's lying just above the frequency or just below in wavelength. Right, so just coming back to this, right? So in wavelength, if we above in wavelength, we see a drop, and below in wavelength or above in frequency, we see a peak, a bump up. And so we can evaluate this looking at the temperature in Kelvin and adopting here a simple model for the intercluster plasma distribution. So the number density is a radial function, right? So you'll have a higher density in the middle and a lower density outside, and you have some normalization and some radial dependence here. And so then our optical depth is going to be proportional to this integration out to some radius, at which point the cluster kind of falls off. And you can do it out to infinity, but you can kind of estimate it just by the size of the cluster as well. There'll be some fiducial factor that sort of dominates there. So you can do this integral, and roughly speaking, this is going to be proportional to this. And so you have some cluster radius, right, which is some defining sort of half light radius, or not half light, but sort of half of the mass of the cluster, or 90% of the mass somewhere is going to be here, and some central number density, and then some factor, and that's going to give you tau, assuming that the cluster is spherically symmetric. And so we can then infer this number density and this radius from Bremsstrahlung observations from X-ray, right? Because the free emissivity is going to go as the temperature and the density squared. And so we can calibrate kind of what this is going to look like by getting the X-ray observation. So we can estimate what the Sunyaev-Zelova signal should be given this sort of distribution. And so we know that we measure our X-ray luminosity, which is proportional to these things. And we also have, we also have a filling factor here, which is basically the ratio of the X-ray emitting volume to the cluster core volume, which might not be exactly 1. And so this allows you to have a variation in NR through the core, which may be important for some clusters because they're not relaxed, or they're more than relaxed, so forth, but it's a small sort of perturbation. And so we have typically a relatively rich cluster will have a luminosity, X-ray luminosity 10 to the 44, and have a cluster radius of about 200 kiloparsecs. And the temperature will be around 4 keV. And so from these, we can estimate what the core density is, which is roughly related to this with this filling factor here. We can estimate what tau is, and it's roughly related to this. And so we can then plug in what our decrement will be. And so it should be proportional to tau times this factor here. We can multiply those through, and roughly we get something which is proportional to the filling factor, to not a very high powered, to this regime. So we should expect from a cluster a temperature decrement of about 1 times 10 to the minus 4. And so we actually, from a pretty massive cluster. And so we typically do see that. This is resolved measurements of the Sunyaev-Zelova from the cluster. And so you can see say the cluster might be rotating. This is on the X-ray center. So you see a slight deviation here in this temperature. This is the differential sky brightness. So you see a boost and a dip here, which might be from some sort of bulk rotation or some asymmetry. But generally, this is the frequency dependency. You see the dip and then the rise. And so many Sunyaev-Zelova experiments will have 3 frequencies. So ACT, for instance, might have 3 frequencies that it observes at. And the idea would be to capture the dip, the sort of regular non-dip, and then the rise here, maybe another observation at low frequencies to get the CMB. And so then they would be able to measure and find clusters throughout, basically massive clusters throughout a sort of redshift independent way. And this ends up being just a mass limited selection because of it's dependent only on the number of electrons along the line of sight. So these are just some measurements of the SC effect at 30 gigahertz from different clusters, showing that these are difference with the CMB already. So these are showing peaks above the CMB, I think. Okay, that's all I wanted to say. Any questions? Just to give you guys a couple of real examples of how inverse Compton might work.
Yes, using this effect, we can study the anisotropies in the CMB, right?
Yes, well, part of them. So there will be a component of anisotropy due to clusters on certain scales. There will also be contributions from the CMB due to cirrus in our galaxy, which is also a problem. And then there may be other anisotropies just in terms of overall mass that might lead to sort of more subtle effects, but they could also, if there were the total mass along the line of sight, you have to have, here you have to have hot electrons, which are upscattering. But anywhere where you had hot electrons along the line of sight, you would have an anisotropy in the CMB.
Thank you.
Any other questions? No? Okay. Easy. If you think of any, we can discuss them on the start of Wednesday's class. Okay. All right. Have a good night, everyone.
Bye bye.
Bye.
Bye-bye.
Tiger.
Bye.